Hello. In today's video, we're going to be talking about Diels Alder chemistry. Diels Alder is one of the most powerful carbon-carbon bond-forming reactions in organic chemistry. You're getting 2 new sigma bonds from this process, and you're also cyclizing a carbon skeleton. So again, this is a very powerful bond-forming reaction in organic chemistry. So the quintessential Diels Alder reaction, and actually one that doesn't technically work, and we'll talk about that in a moment, is a diene, a butadiene, with an alkene like ethylene, and this will cyclize to give you a 6-membered ring, notice with a double bond in it. So let's look at how that works, and we're going to look at examples as well. So the arrow pushing mechanism for this reaction, I'm going to go ahead and highlight use some color coding to keep track of where electrons are going. What you do is you draw arrows to the space between the carbon-carbon bonds, and this is how you form a sigma bond. And this pi system, these electrons go here, these ones go here, these ones go here. You notice the arrow pushing mechanism can actually go in either direction, so you can draw them either going, in this case, in the clockwise fashion. You could also draw them counterclockwise. We refer to this as a 4+2 cycloaddition. And there are 2 different styles of brackets or things you can use. You can use parentheses or brackets. When you use parentheses, it technically refers to the number of atoms. So you have 4 atoms on this side and 2 atoms on this side. If you use brackets, it's referring to the number of electrons for this cycloaddition. And cycloadditions are a very large class of organic reactions. Diels Alder is one particular type of cycloaddition. It's a good entry point into understanding cycloadditions. You've likely seen it before in the ozonolysis reaction as well. That's also a cycloaddition. Okay, so the bracket means it's the number of electrons. So there are 4 electrons on this side and 2 on this side. So in this case, the 4+2 could refer to either the number of atoms or the number of electrons. All right, let's look a little bit more into what's going on. So if you look at the nature of this butadiene, and you look at the orbitals associated with the pi system of the butadiene and the pi bond of the ethylene, you can see that there is that you have shading and lack of shading. So this implies that these are in phase. So when orbitals are in phase, they can form a bond. So again, these are in phase and these are in phase. So you can imagine this butadiene is kind of coming like a sandwich on top of the ethylene. And so let's look at why I drew the orbitals the way I did. So if you look at the pi energy orbital diagram, you have 4 p orbitals that went into forming this butadiene, and so you end up with 4 new pi orbitals, or pi orbitals in the pi system. There are 4 electrons in this system, 2, 4, and so we go ahead and draw in that there are, again, 4 in this energy diagram, leaving 2 orbitals that are not occupied. Similarly, for the ethylene, we do the same thing, where we started off with 2 p orbitals, we get 2 new orbitals out. Again, our orbital math is always the number of orbitals in, gives us the number of orbitals out, and there are only 2 electrons in this system. We refer to the molecule that has 2 alkenes, or 4 orbitals, as the diene, and the other system as the dienophile, and I will refer to them that way moving forward. Dienophile means simply that it likes or wants a diene. Okay, and so we have 2 options for how this can react. You can either put the electrons from the diene into the dienophile, so you always have to interact filled orbitals with empty orbitals, or you can interact the filled orbital of the dienophile with the empty orbital of the diene. So in this case, we go with the diene orbitals interacting with the dienophile orbitals because they are closer in energy. And so whichever one is closer in energy, that's how the reaction is going to proceed. When we're looking at how to think about why this is drawn this way, the lowest orbital of a diene or of an alkene system is always going to have 0 nodes. So this has 0 nodes across it. And the next energy level up has 1 node. So you notice there's a node right here. If you look at the diene, there's going to be more complex orbitals, but the lowest energy orbital is going to have 0 nodes, similar to this one down here. The next level up is going to have 1 node. It's going to be right in the middle. It needs to maintain symmetry, and that's the one we're looking at here. The next energy level up is going to have 2 nodes, and the highest energy level is going to have the maximum number of nodes, in this case 3 nodes. We don't have to worry about those, or what those look like as much for this case, because because we're not interacting with those orbitals. But that's what they look like. Let's go on to look at some reactivity of how to make Diels Alder reactions more reactive. I told you these ones are not terribly reactive, but let's make them more reactive. So one way to make a diene more reactive is to restrict its motion. So a diene will naturally sit in 2 forms. You can rotate around this bond. It can maintain being conjugated. When it sits in this form, it's called the S-trans. And you notice that these 2 carbon atoms are actually really far apart from each other. They're not forming that C shape that is kind of required to make the carbon-carbon bond. So when it exists in this S-trans form, it's not reactive. So what we want to do is force it into the S-cis form. And one way of forcing it into the S-cis form is actually to just simply make it into a ring. So if we add an oxygen atom or a carbon atom, pretty much any atom here, this will lock the S-cis form into place, which is going to allow the reaction to proceed better. Another thing that we can do to make the reaction go better is that we can add an electron donating group. So by putting an oxygen here, we're going to donate electron density. You can think about resonance structures donating electron density. That's going to push these energy levels up on the diene, which is going to push this highest occupied orbital in closer proximity to this lowest unoccupied. So we refer to this again as the HOMO, or the highest occupied molecular orbital. This would be the lowest unoccupied, or the LUMO. So again, we're pushing them closer in energy together. If we look now on the dienophile side, if we have a simple dienophile, ethylene is not terribly reactive. But if we put an electron withdrawing group on this, that's going to lower the energy of these electrons, or of these orbitals, and by lowering these energy levels, they're going to be closer in energy to the diene, and the closer they are in energy, the better the reaction, or the faster the reaction. Let's look now at what happens when we have to think about the regiochemistry, or the regiochemical outcomes of these reactions. So I've flipped this diene in 2 different orientations. The dienophile, just for the ease, I'm keeping oriented in the same way. So let's look at the 2 different products that could form from these reactions. And we're going to figure out which of these 2 products is most likely to form. So again, you could either have this oxygen, the methyl ether, on the same side, or on the opposite side, or the same side of this 6-membered ring as the ketone. So the best way, in my opinion, to do this is to look at our whatever atom you have that has a strongly polarized bond. In this case, the oxygen. It's polarized, so you have a delta negative, and you have a delta positive then on the adjacent carbon. You can move that around: delta negative, delta positive, delta negative, delta positive. Similarly, you can do that with the dienophile: delta negative on the oxygen, delta positive on the carbon, negative on this carbon, positive on this carbon. So it's a similar strategy that we used for aromatic reactions. You can look to the aromaticity video to learn more about that. But this tells you that you are going to have an overlap of negatives and positives. And of course, negatives and positives interact better than trying to push 2 negative ends of a magnet together. And so this is the more favorable interaction, where you have negative and positive, as opposed to negative and negative. So this is the regiochemical outcome that you would predict for this process. Let's now look at the stereochemical outcome. So there's all these different layers of Diels Alder chemistry to be able to understand how best to react for Diels Alder reactions. So in this case, you notice I've replaced the oxygen for a carbon. This is a very reactive diene called cyclopentadiene. This particular diene is so reactive it reacts with itself to give a dimer of itself, but you can do what's called cracking this dimer. You often buy this as the dimer. You can crack it, and it undergoes what's called a retro or a backward Diels Alder reaction that gives you the diene. So the arrow pushing for that, there are 2 molecules of this purple in this dimer, and again, so you'll get 2 equivalents of this diene out of this reaction. So now let's look at the reaction of this diene with this dienophile. And again, look, I've added an electron withdrawing ester group on the dienophile. So the diene is going to interact with the dienophile. It's going to form new carbon-carbon bonds, and it's going to have this double bond. The telltale sign of a Diels Alder reaction is a 6-membered ring with a double bond in it. That is a pretty good giveaway that it's going to be a Diels Alder reaction. Okay, so now we have to look at the relative stereochemistry of this group, this bridgehead group, and this ester. It's going to be either up or down. So let's just assume that the bridgehead is going to go up. It could have also gone down, and the opposite logic is also true. There are 2 possible outcomes of this ester. One where it's going up, and the other where it's going down. The up we refer to as exo, the down we refer to as endo. Let's look at the 3-dimensional form of that to see kind of why it might be called that. So exo, this ester is kind of sticking away from the cavity that's formed down here. Endo, this ester is now facing down. What's interesting is, and perhaps counterintuitive, is that the endo form is actually the major product that is often formed for Diels Alder reactions. So let's look at why that's the case. So why endo? So you're going to get to the question of why endo, we have to look back at the diene interacting with the dienophile. But our dienophile is a little bit more complicated. This ester plays a role in how the dienophile is going to interact. That ester, the p bond, the p orbital of the carbonyl carbon, could either be on this side or on this side. So if it's on this side of the dienophile, this would give us the exo product. If it's on this side, it gives us the endo product. Notice that when it's on this side with the endo product, this gives us what I refer to as a bonus interaction. It's also referred to as a secondary orbital interaction. And this secondary orbital interaction is going to stabilize a little bit. And because it stabilizes the transition state, that transition state now dictates the product, the major product of this, again, being the endo product for the Diels Alder reaction. Let's now look at a challenging problem. We're going to go through all of the factors that we just learned. So if you were asked to mix this diene with this particular dienophile, the first thing you would look at is the fact that this is indeed a 4+2 reaction. So a diene and a dienophile. Let's look at the regiochemistry first. So regiochemistry, we'd use our delta negatives and delta positives, and we'd find that this carbon on the end would match up with this carbon here, the delta negative to delta positive. This delta negative would interact with this delta positive. So let's go ahead and redraw our diene and dienophile in a way that's going to allow us to get at least the right regiochemical outcomes for products. Now we could draw our arrow pushing mechanism. If you're asked to do that, it's a good idea to go ahead and draw those arrows. There are 3 arrows because there are 6 electrons total moving around, 2 forming new sigma bonds and 1 forming a new pi bond. Now let's look at the stereochemical outcome. First off, we have to see, is there a p orbital for a secondary orbital interaction? And indeed, in a nitrile or a cyanide, there is a p orbital on that carbon, so secondary orbital interactions are in play. And so that means the product is going to be endo. So let's go ahead and draw the 6-membered ring, put a double bond in it, and start to orient where our items are going to be. You notice we have not drawn stereochemistry yet. We're going to figure out where that is. What I like to do in this case is I like to draw in kind of a fake bond, in this case a purple bond, to make a cyclic form, because in my opinion it's a little bit easier to see these things as bicyclic structures. So these purple bonds are going to be coming out of the board at us, similar to what we did on the previous page. Note that this box doesn't really exist. It's just helping us keep track of what is endo versus exo. So if this is coming out at us, then that means that this bond would have to be going away from us. So this methoxy is going into the plane of the board. We've already established, because the secondary orbital interactions, that the product is going to be endo, which means that this is going to be going back as well, as compared to this bridgehead, this fake bridgehead that we've drawn in here. That's how we define it as endo. Now what about this methyl group? Well, this started off its life as an E, or a trans alkene, and the geometry of the alkene is going to get locked in the final product. So these two groups are going to be trans to each other, and that means that this methyl is going to be coming out of the plane of the board at us. So now we can remember that instead of this box that I drew in, there are actually hydrogen atoms there, protons, which we actually won't even draw in our final product, which we would fill in here, where these two groups, the methoxy and the nitrile, are cis to each other. The nitrile and the methyl group are trans to each other. Okay, we're going to go one step deeper into this, beyond normal Diels Alder. A lot of classes don't actually discuss going beyond normal, but let's go ahead and go down this journey. So we've already spent all the time discussing these orbitals and this overlap and which one's closer. So let's look what happens when we have an electron donating diene, an electron withdrawing group on the dienophile. That's how we described our normal. You could also have an electron withdrawing group on the diene, an electron donating group on the dienophile. So what's going to happen is that these orbitals are kind of going to switch places, where this orbital starts to become closer in energy to this orbital than the other way around. So if you look at the reaction rate, as you start to move these away from being a good electron donating, electron withdrawing pair, your reaction rate is going to go way down. But as you start to invert the electronics, so you have electron withdrawing on the diene and electron donating on the dienophile, the reaction rate is going to go up again. So we refer to this side of things as an inverse electron demand Diels Alder, and the side we've been talking about for the rest of this video is all considered normal demand. So again, inverse demand Diels Alder reactions are also a very powerful tool for the synthetic organic chemist. The last thing I want to note before we close off on Diels Alder chemistry is that these do not have to all be carbon atoms. We refer to systems that don't have all carbon atoms as hetero Diels Alder processes. And these are also, again, very powerful bond-forming processes. They don't give you six-membered carbon rings, but they can give you six-membered rings that have nitrogen, oxygen, sulfur, lots of other atoms involved as well. All right, well, that was a lot to take in. Thank you for your time, and thank you for this long video, and I hope this was useful to you.